This is a quick recap video of chapter Thermodynamics. So let's start with the definition of thermodynamics. It is the branch of science that deals with the concepts of heat and temperature and the interconversion of heat and other forms of energy. Next is thermodynamic system, an assembly of a very large number of particles having a certain value of pressure, volume and temperature is called a thermodynamic system. Surroundings. Everything outside the system which can have a direct effect on the system is called its surrounding. Thermodynamic variables. The quantities like pressure, volume and temperature which help us to study the behavior of a thermodynamic system are called thermodynamic variables. Equation of state. The mathematical relationship between pressure, volume and temperature of a thermodynamic system is called the equation of state. For example, the equation of state of n moles of an ideal gas can be written as PV equals to nRT. Next is thermal equilibrium. Two systems are in thermal equilibrium with each other if they have the same temperature. Thermodynamic equilibrium. A system is said to be in the state of thermodynamic equilibrium if the macroscopic variables describing the thermodynamic state of the system do not change with time. A system in a state of thermodynamic equilibrium possesses mechanical, thermal and chemical equilibria simultaneously. Now, state variables. The macroscopic quantities which are used to describe the equilibrium state of a thermodynamic system are called state variables. The value of a state variable depends only on a particular state, not on the path used to attain that state. Pressure, volume, temperature and mass are state variables, and heat and this work are not state variables. Now, next is zeroth law of thermodynamics. If two systems A and B are in thermal equilibrium with the third system C, then A and B are in thermal equilibrium with each other. According to this law, temperature is a physical quantity which has the same value for all the systems which are in thermal equilibrium with each other. Now, next is internal energy. The internal energy of a system is the sum of molecular kinetic and potential energies in the frame of reference relative to which the center of mass of a system is at rest. It does not include the overall kinetic energy of the system, and it is a state variable denoted by U. Now, next is quasi-static process. A quasi-static process is an infinitely slow process such that system remains in thermal and mechanical equilibrium with the surroundings throughout. In such a process, the pressure and temperature of the surroundings can differ from those of the system only infinitely small. Next is isothermal process. A process in which temperature remains constant is called an isothermal process. For such process, PV is equals to constant, or we can say that P1 V1 will be equals to P2 V2. Next is adiabatic process. A process in which the thermally insulated system neither loses or gains heat from the surrounding is called adiabatic system. And equations of state for adiabatic process are: first is PV to the power gamma is equals to constant, or P1 V1 to the power gamma is equals to P2 V to the power gamma. Next is TV to the power gamma minus 1 equals to constant, or T1 V1 gamma minus 1 will be equals to T2 V2 gamma minus 1. And the last equation is P to the power gamma minus 1 upon T to the power R will be equals, this is gamma, will be equals to constant, or P1 to the power gamma minus 1 upon T1 to the power gamma is equals to P to the power gamma minus 1 upon T to the power gamma, where gamma is Cp upon Cv. Now, next is isobaric process. A process in which volume remains constant is called isobaric process. For such process, V upon T is equals to constant, or V1 upon T1 is equals to V2 upon T2. Now next is isochoric process. A process in which the volume remains constant is called the isochoric process. For such process, P upon T is equals to a constant, or P1 upon T1 is equals to P2 upon T2. Next is indicator diagram, a graphical representation of the state of a system with the help of two thermodynamical variables is called indicator diagram of the system. The graph between the pressure and volume is called PV diagram. Now, work done during the expansion of a gas. When the volume of a gas changes from V1 to V2, the work done is equals to this is integration of P dV, which is equals to area enclosed between the PV curve and the volume axis, and this limit is from V1 to V2. Next is work done during a cyclic process. From the PV diagram, work done per cycle is equals to the area of the loop representing the cycle. Now first point is, if the loop is traced clockwise, the work done is positive and work done is by the system. Now second point is, if the loop is traced anti-clockwise, the work done is negative and work is done on the system. Now first law of thermodynamics. It states that if heat dq is given to a system, a part of it is used in increasing the internal energy by an amount du, and the remaining energy is used in doing the external work dw. It is just a restatement of the law of conservation of energy. Thus dq is equals to du plus dw, or dq will be equals to du plus p dv. Now let's understand sign conventions used for this. First is, heat absorbed by the system is positive and heat given out by the system is negative. Second point, increase in internal energy of a system is positive and decrease in internal energy of a system is negative. And last point is, work done by a system is positive and work done on a system is negative. Now next is work done in an isothermal process. Work done when 1 mole of a gas expands isothermally will be equals to 2.303 RT log V2 upon V1, which will be equals to 2.303 RT log P1 upon P2. Now next is work done in adiabatic process. Work done when 1 mole of a gas expands adiabatically and its temperature falls from T1 to T2. Then this will be equals to R upon gamma minus 1 in the bracket T1 minus T2. Or this will be equals to 1 upon gamma minus 1 in the bracket P1 V1 minus P2 V2. Now next is Dulong and Petit's law. Near the room temperature, the molar specific heat of most of the solids at constant volume is equals to 3R, or 6 calorie per mole per Kelvin, or 25 joule per mole per Kelvin. This statement is known as Dulong and Petit's law. Now next is molar specific heat of a gas as at constant volume. It is defined as the amount of heat required to raise the temperature of 1 mole of the gas through 1 degree Celsius at constant volume. If Cv is the specific heat of gas for 1 gram at constant volume and capital M is its molecular weight, then molar specific heat at constant volume is given by Cv is equals to M into small cv. So now next is molar specific heat of a gas at constant pressure. It is defined as the amount of heat required to raise the temperature of 1 mole of the gas through 1 degree Celsius at constant pressure. Thus Cp will be equals to M into small cp. Next is relation between two specific heats of a gas. Specific heat of a gas at constant pressure is greater than the specific heat at constant volume. So for 1 mole of a gas, first Cp minus Cv is equals to R, where Cp, Cv are in units of work. Second, Cp minus Cv is equals to R upon J, where this Cp and Cv are units of heat, where this R is the universal gas constant for 1 mole of a gas. Now, for 1 gram of a gas, first Cp minus Cv is equals to R, where Cp and Cv are units of work. Second, Cp minus Cv is equals to small r upon J, where the Cp and Cv are units of heat, and this small r is equals to capital R upon capital M, which is equals to gas constant for 1 gram of a gas. And now clearly heat lost or heat gained by n molecules of a gas. First, at constant pressure, Q will be equals to n Cp delta T, and second, at constant volume, Q will be equals to n Cv delta T, where this n is equals to number of moles of gas, which will be equals to mass of a gas upon its molecular mass. Now, next is heat engine. It is a device which converts continuously heat energy into mechanical energy in a cyclic process. It essentially consists, first, a source of heat, second, a sink of heat, and third, working substance. Now, next is efficiency of a heat engine. It is the ratio of useful work done, capital W, by the energy per cycle to the heat energy Q1 absorbed by the source per cycle. So this eta will be equals to work output upon heat input, which will be equals to capital W upon Q1, which will be equals to Q1 minus Q2 upon Q1, and finally which will be equals to 1 minus Q2 upon Q1. Now, next is second law of thermodynamics. First, Kelvin-Planck statement. It is impossible to construct an engine which will produce no effect other than exerting heat from a reservoir and performing an equivalent amount of work. And second, Clause's statement. It is impossible for a self-acting machine unaided by an external agency to transfer heat from a body to another at higher temperature. Now, next is reversible process, a process which can be made to proceed in the reverse direction by the variation in its condition, so that any change occurring in any part of the direct process is exactly reversed in the corresponding part of the reverse process is called a reversible process. Irreversible process, a process which cannot be made to proceed in the reverse direction, is called irreversible process. So now next is Carnot's engine. It is an ideal heat engine which is based on the Carnot's reversible cycle. Its working consists of 4 steps. First is isothermal expansion, second is adiabatic expansion, third is isothermal compression, and fourth one is adiabatic compression. The efficiency of a Carnot engine, this eta will be equals to 1 minus Q2 upon Q1, which will be equals to 1 minus T2 upon T1, where this T2 and T1 are temperatures of the source and sink. This is the temperature of T1 is the temperature of source and T2 is the temperature of sink. Next is Carnot theorem. It states that first, no engine working between two given temperatures can have efficiency greater than that of Carnot engine working between the same two temperatures, and second is the efficiency of Carnot engine is independent of the nature of the working substance. Next topic is refrigerator. It is a heat engine working in the reverse direction. Here working substance absorbs heat Q2 from the sink at temperature T2. An external agency does the work on the working substance. A larger amount of heat Q1 is rejected from the source at higher temperature T2. So Q1 will be equals to Q2 plus capital W. And the last topic is coefficient of performance. It is defined as the ratio of the amount of heat Q2 removed per cycle from the contents of the refrigerator to the work done capital W by the external agency to remove it. So beta will be equals to Q2 upon W, which will be equals to Q2 upon Q1 minus Q2, and finally which will be equals to T2 upon T1 minus T2. Thank you.